was waiting for a slide.
Sorry, folks, just some momentary technical difficulties. We'll be back on here shortly. There we go.
Okay, so I'm going to talk about something that's sort of very old hat in some sense. I mean, OSPF version 2 has been around for 15, 20 years. I'm just going to talk a little bit about some of the things we've discovered with what happens with OSPF routing, especially with areas. So a brief introduction. So OSPF is widely used for routing within an autonomous system. It routes packets along shortest paths in terms of weights that are configured on the links. For scalability issues, OSPF at least allows the division of a domain into areas that affect the routing. This is to, in some sense, reduce the amount that an individual router has to know about the entire network. Areas are, at least in my experience, used widely where people are using OSPF. Areas add some surprising complexity to what happens with OSPF routing. You can get paths that are no longer shortest paths in terms of the weights. And the OSPF has evolved to allow some additional tweaks that make the complexity even greater. I'm going to give a quick introduction to OSPF routing, how areas behave with routing, a couple of the RFCs that have tweaked on the OSPF standard, and about some other things that happen with routing to autonomous system border routers. And I'm going to end with a quiz, just to get us back to very old school. Okay, so OSPF is a link state protocol. So every router learns the topology of the network or the piece of the network that it's really paying attention to, computes shortest paths in that network, and then forwards packets along those shortest paths. OSPF does this type of link state protocol with a couple of tweaks. There are two different major types of nodes. There are transit nodes, which is nodes where traffic is going through, and stub nodes, which are essentially loopbacks or subnets that are advertised by the routers. And so links between transit nodes are only actually used if they are up in both directions. Links to stubs are one-way links going to the stub, and that's all traffic is really heading to a stub in its long run. Okay. So here's an example, and this will sort of illustrate a type of figure that I'm going to use for many of these examples. So this is a sketch of a network. Those big black boxes with names in them are routers. At the bottom of the box are some loopbacks on the router and their configured OSPF weight or distance to the loopback. The links between routers are the transit links, and the little boxes on the links are the configured OSPF weight or distance on those links. It's configured in both directions, so actually in all of the examples it's going to actually be symmetric weights, and so you don't really need to worry about the fact that there are two weights on them. So, for example, if you were routing from the back 1 to the access 3 router, the various routers would be computing their paths and distances to the destination. So from access 3 itself, the distance is just 1 because it's just this distance from it to its loopback. Back 4 looks amongst its various routes and finds the shortest path of 51, which is along the direct link. Just pick another example. Back 3 has the indirect route through back 4, which is cheaper than its direct route. And so all the routers, compute their distances, and then each router in turn forwards the packets along its shortest path or paths. So for scalability, OSPF domains can be divided into areas. Areas are just numbered with, well, you can either think of it as an integer or an IP address. They're often represented as IP addresses. Conceptually, areas work as a hub and spoke network. So area 0 is the hub. All of the non-zero areas form spokes. An area is really just links are what are in areas. Links and stubs are in areas. Routers can end up being in more than one area if they have links that are in more than one area, but the links are what are in areas. If a router has links in multiple areas, it's an area border router. And at least if you start with just the base OSPF version 2, an area border router must have links in area 0. And that is because it will only pay attention to stubs that are not in attached areas from area 0. So if it doesn't have them, it'll, yes. So how this sort of limits the set of knowledge is that a router only learns the topology of the areas it's directly connected to. And for things that it's not directly connected to, it learns the area border routers basically announce their distances to those remote stubs in those other areas. So for example, in this, I've indicated the different areas by different colors. So black is going to be area 0. Other colors are non-zero areas. So we can see there that we have three different areas: the red area, the blue area, and the black. The stubs also are in areas, and so they're also indicated by the color they're in. Okay, and in this situation, the four back routers are the area border routers because they're the routers that have links in more than one area. Okay, so for path calculation with areas, routers calculate shortest path trees to all of their attached, the stubs that are in their local areas, their intra-area paths. And then for destinations that are not in one of their locally attached areas, they look at paths to an area border router plus the distance the area border router advertised and pick the shortest of those, leading to inter-area paths. So for example, similar network with the areas, if we were routing from access 3 to access 1, the area border routers that see that stub on access 1 are just back 1 and back 2. And so they compute their intra-area paths to that. Then the area border routers back 3 and back 4 compute their shortest paths by looking at paths to one of the area border routers that's advertising distances there. And then the source router looks at computing its distances. And in this case, it looks at either the path going, it looks at its path to the area border routers and picks the closest one, which ends up being the loop through back 4 and back 3. Okay, so this issue that the routers will always pick an intra-area path over an inter-area path can lead to a type of area hijacking, where the path will end up following something that's different than what the earlier routers were calculating their distances based on. So as an example, in this network, once again, same source and destination, if the red link between access 1 and back 2 goes down, well, let's look at what happens to the routing. So first of all, back 2 is now going to shift to a longer path to its destination, because in the red area it has a path that goes through that zigzag, and so it will advertise that greater distance. Back 4, when it wants to compute its shortest path, sees that it has now a shorter path by going from back, through back 2 to back 1, and then using the distance that back 1 advertised. And then once again, access 3 in the blue area will compute its path using back 4. And so this means that it computed a path and distance that was based on this path. But when the traffic reaches back 2 will discover that it has an intra-area path and use that instead of forwarding to back 1 along the shorter path. And so the actual traffic will zigzag through one of the access routers on its way to the other one. So this is sort of a well-known phenomenon. And so one of the ways to address it would be if the link between back 1 and back 2, or if you had a parallel link that was in the red area, then it would be able to use that for its route. That creates a problem with trying to create lots of extra parallel links. And so RFC 5185 allowed configuration of a link to be in multiple areas. So stubs still can only be in a single area. Links can be configured in multiple areas and having only one primary area, which is the area where the actual interface IPs are advertised as being in. And so this allows configuration against some hijacking cases, but also adds some complexity. For example, in this network, now that there is that the link between back 1 and back 2 is also in the red area, back 2 sees an intra-area path in the red area going to back 1 and then to access 1 and avoids the zigzagging. But this can also lead to other complications, as we'll see a little later. So there's also another type of hijacking. Oh, sorry, I'm getting ahead of myself. So another type of thing that can happen with areas. This is a simple two-area network. One thing that areas are often used for is to configure a different area in each office or POP. And so that's what this is sort of representing, is two separate access networks connected by a backbone. And if you're routing from the source to destination, it takes a very straightforward route. Now, however, suppose that access to's connections to the aggregation routers happened to share the same pathway. So there was a lack of fiber diversity. And so somebody had the clever idea of putting in a backup link from access to over to another aggregation router to get some diversity. Configure it with a very high OSPF weight so that it would not be used unless there was a, for example, fiber cut that would threaten to disconnect access to. Well, this has the disadvantage that makes aggregator 2 become an area border router because it now has links in multiple areas. As an area border router, it only will listen to remote prefixes, remote stubs in area 0. It doesn't have any links in area 0, so it doesn't learn about the destination stub, and so it just black holes traffic. So a way around this was introduced with RFC 3509, which was basically the observation that, well, routers could actually do something sensible in this case rather than just black holing the traffic. This is sort of a very strange RFC because it doesn't actually specify what the standard should, an amendment to the standard or an option. All it says is that in this case, specific router vendors have done something different than black hole the traffic. They allow for a concept of a multi-area router. And it specifies what Cisco and IBM routers do. And that's the only two vendors' routers it specifies what happens to. And they specify slightly different behaviors for that. But the basic point is that it says that they can essentially act as if they are just routers with the areas being separate and not acting as an area border router. So they can still forward traffic to other prefixes that they've learned. So that allows the routers to still forward traffic to that previous destination, but it can still create other pieces of chaos. So in that same network, if we were routing from access 1 to access 3, once again, the route would be a fairly straightforward one, up to the backbone and across and back. Now, if we introduce that same sort of backup link with a very high OSPF weight, well, aggregator 2 doesn't black hole the traffic because if it's complying with RFC 3509 because it acts as a multi-area router instead of an area border router, but it does now have a local path in the blue area, intra-area path to the destination. So instead, it will route traffic over this backup link through one access router to the other. Okay. Another example of some interesting things that happens there is that the stub area can matter. So what area the stub is in can certainly have an impact. So here's another example. a access network, if we're routing from access 1 to aggregation 1, you might think that it would take the nice short hop of length 50. However, let's look at what happens in more detail. There's only 2 area border routers in this, back 1 and back 2. So they compute their distance to the red stub in the red area by looking at their shortest paths. And then source computes in the blue area its routes to ABRs plus the ABR distances. And so it sees the route to back 1 plus the distance of 351 that the black 1 advertised and gets its distance of 751, or it can see the route going up through back 2 plus back 2's advertised distance. And the route through back 2 is the shorter one. So it'll forward its traffic towards aggregator 2. But when the traffic gets to aggregator 2, it now sees that it has an intra-area path in the red area, so we'll forward directly there. So you get up with this another type of hijacking that results in this a little bit unusual looking path. So one last thing that happens is that routers can import external routes, either static routes or they can import routes from other routing processes, either OSPF or other types of cooperating processes. When a router imports external routes, it's called an ASBR, for Autonomous System Border Router. And so the ASBR advertises that it has a given prefix at a given distance that it can forward traffic to. And when a router is looking for paths, it first looks to see if it has an intra-area path. Then it looks for an inter-area path within the domain. And then it looks to see if it has a path to an external stub. And once again, it's looking at the distance to the ASBR plus the distance that the ASBR advertised. Now, the one thing that's unusual about this is that unlike all of the loopbacks that you could be routing to, ASBRs are routers, and therefore they're not in a specific area. And therefore you could have intra-area routes in multiple areas. And so there has to be there is an additional tiebreak for routing to an ASBR. And it actually depends on, there's anything of whether RFC 1583 compatibility is set to disabled or not. But it basically breaks ties by lowest cost, and then if there's a tie on cost, it breaks ties by routing along the higher area number. So for example, if we were just routing from back 1 to back 2, well, it depends on whether we're routing to it as the loopback or routing to it as an ASBR. If we're routing to it as a loopback, the stub is in the black area, so it's going to use the intra-area path in the black area. If we're routing it to it as an ASBR, then it sees that it has a shorter route in the red area and routes by way of the access routers in the red area. Okay, so as promised, there's a quiz, which is what's the path from R1 to R5 in this network? Give a pause if anyone wants to try to venture a guess. And actually, I'll jump ahead. It's a trick question because the answer depends on what the question was. So it depends on whether the destination meant the area 0 loopback, or the black area loopback, the green area loopback, or the destination as an ASBR. It also depends on whether the routers are RFC 3509 compliant. And if they're RFC 3509 compliant, it depends on whether they're Cisco or Juniper routers at least, because they behave differently. In particular, when you have a multi-area router, it depends on whether they advertise local prefixes or not. So now we can go through the various depends. So if we're at routing to the area 0 loopback, and the R1 is not RFC 3509 compliant, it will black hole the traffic because it will be an area border router and will not have seen that loopback advertised. On the other hand, if it's RFC 3509 compliant, you get this path. It will first forward in the red area, then split amongst the red and blue area links, and then go across the green link. Now, if you're routing to the green stub, as we said, it depends on whether the R3 is a Cisco or a Juniper. If it's a Cisco router, it will end up doing the same path we saw for the black stub. However, if it's a Juniper router, it'll end up doing a sort of different path, where it splits along the first link and then just uses the blue area. If it's routing to an ASBR, it doesn't really matter whether Cisco or, yeah, sorry, it does matter, right. So for the ASBR routing, once again, depending on whether Cisco or Juniper, you'll get this 3-hop path or that one. So, thank you.
Okay, any questions? Going once, going twice.
IAJ. Aside from sticking with ISIS, what's the takeaway?
So the takeaway is really that areas
Don't build networks like that.
It's sort of that you need to, it's more complicated than you might expect. And so if you're using OSPF with areas, you need to be ready for surprises. Right, and so I guess, yes, I have some friends that have claimed that the takeaway is that use ISIS because areas are so complicated there that no one ever uses them, and so you don't have to worry about them. They're actually called
Or
areas.
ISIS scales so much better that you don't need to.
There's also that, yes.
Okay, anybody else? Okay, David, thank you very much.
Thank you again.